In this video, we're going to talk about the iteration matrices. This will be useful in the next section and also in the next chapter when we'll be dealing with parabolic PDEs. Let me define a linear recurrence relation. If you consider a matrix M, which is Q by Q, and two vectors B and X naught, which are in RQ or CQ, then you can define the sequence Xn as Xn plus 1 equals M times Xn plus B. This will be called a linear recurrence relation, and M will be called the iteration matrix. Now, what we will do is define a convergent numerical method simply by considering a linear recurrence relation, as we've just did, with an iteration matrix M, and a set of possible initial conditions C that will be included in RQ or CQ, and that, of course, will be non-empty. Now, we will say that we have a convergent numerical method if for all possible vectors B, then we will have this sequence Xn plus 1 equals Mxn that will provide us with a Xn that converges. Now, we will consider a convergent numerical method, and we will call x the limit of xn, and en the difference between the term xn and its limit. And what we want to characterize is how fast does xn go to x. And that will be en, the difference, and that will be called the convergence rate. Now, you see why this is interesting, because if you have a numerical method, a sequence that converge towards something of interest, you want to know whether you're going to reach this something of interest quickly or not so quickly. So this is why the convergence rate becomes useful and interesting. Let me give you an example. Very simple example. You consider Q equal 1. In other words, the matrix is really a scalar number. So what you consider is Xn plus 1 equals Mxn, something you know very well. It's called the geometric sequence. And the numerical method will converge if and only if the absolute value of the modulus of M is smaller than 1 strictly or equal to 1. And if the absolute value of modulus of M is strictly smaller than 1, then we will have En, which is M raised to power n x naught. In other words, the convergence rate will be the absolute value of M. Now, if instead of being in dimension 1, we are in dimension Q, then basically here are four statements that are equivalent. The first one says that for all x in RQ or CQ, the sequence xn that has been defined as x naught equals x and xn plus 1 equals mxn will converge toward 0. The second statement is saying that the limit of the nth power of the matrix is 0. The third statement states that the largest possible eigenvalue of n in absolute value, in other words, the spectral radius, is strictly smaller than 1. And finally, the fourth statement says that there exists an induced norm such that the norm of m is strictly smaller than 1. Now, again, there will be two applications of this. The first application is coming in the next section, and that will be when we will be solving linear system with iterative methods. And the other application is coming up next week in chapter 8, when we will be discussing parabolic partial differential equations.